Hello, James Flaten here with the Minnesota Space Grant Consortium with some introductory remarks about stratospheric weather ballooning. Let me share my screen. I won't read through this entire abstract, but basically, weather ballooning refers to using balloons used by the Weather Service. These happen to be latex balloons. And stratospheric ballooning means flying balloons into the stratosphere. You can use other kinds of balloons to do that as well, but we're doing stratospheric weather ballooning in the nationwide eclipse ballooning project, NEBP. So with such balloons, whether you fill them with helium or hydrogen, both good lift gases with different issues, you can carry payloads into the stratosphere so as to study the stratosphere, so as to study the Earth, or at least take interesting pictures. And so in the case of NEBP, for instance, the atmospheric sciences side will carry small radiosondes to send weather data to a ground station on the ground. And the engineering side of NEBP will carry video streaming equipment to try to get the view from the stratosphere to the ground in real time. The eclipses, of course, are during October of 2023 and April of 2024. So let's take a look at a montage from a specific stratospheric ballooning flight. If when you click on this link, I'll show you a link to where these slides are located at the end of this video. If it's choppy in my video, just go and click on the link directly yourself. So here we are releasing a weather balloon. So those are payloads. And when I let them go, the balloon, which is above, will lift them. There's a parachute up there as well, and fly into this environment. This is the stratosphere. It looks a lot like outer space. The next view is actually an up-looking view of the balloon itself. I'm going to stop at that moment and take a quick look at the balloon bursting. Okay, so the balloon, which was about 8 or 9 feet across when we let it go, was more than 30 feet across at this point in the flight. Basically, it stretched a lot. And then, of course, after the balloon bursts, everything starts to fall. There's a parachute up there which will open up, and this particular flight landed more than 100 miles away from where it was released. Okay, back to my slides. In the case of NEBP, the atmospheric sciences side is going to use small balloons, relatively speaking, 200-gram approximately weather balloons. And so on the left-hand side, you see one of those balloons inflated enough to carry a small radiosonde device. The video streaming side, on the other hand, will use bigger balloons, 1,600-gram weather balloons. And so on the right-hand side, you see a stack of several payloads, one of which is a video streaming payload. And let's take a look at the launch of both of these. So here we go. Here's the release of the radiosonde. So one person holds the balloon, one person holds the radiosonde. And although they're only a few feet apart at this moment, as the radiosonde goes up, it actually unwinds so as to get farther and farther away from the balloon and stay out of the wake, the disturbance made by the balloon, and get better data. The information from the radiosonde is sent to the ground by radio to a ground station, so you don't actually have to get these ones back. Here now is the release of the video streaming stack. And so one comment about this release, it turns out the parachute, which is right next to the first person carrying a payload, who is next to that person holding onto the balloon, the parachute was on a hook and it came off the hook and it immediately inflated upside down. That was a mistake, but other than that, this is a fairly representative launch. So you let go of the balloon and then it picks up the payloads one at a time and carries them away. But the parachute is not supposed to be open on ascent like that. Okay, back to my slides. A few comments about weather ballooning in general, and you'll need to learn how to do these in more detail. This is just an introductory video. So for instance, when you have your stuff ready to fly, here are some steps for conducting a weather balloon mission. You will definitely do flight predictions. In other words, use Weather Service wind predictions to figure out approximately where your balloon will go, okay? And then to choose an appropriate launch site, possibly chosen so that it lands somewhere fairly specific. especially if you're trying to get it back. You don't want it to land maybe out at sea or land in the mountains. You want to launch so that it lands someplace that you can reach. You'll need to go to the launch site, set up, inflate the balloon to a specific amount of lift. So in this case, the lift can be thought of as enough lifting gas to lift the balloon itself, plus more, enough to lift the stack, plus more, enough to make sure when you let go, it actually goes up at a reasonable rate. So getting the lift just right can be tricky if it's windy. You need to seal the balloon once it's appropriately filled. This is a little more complicated if you have a vent on it. And then you will attach the payload stack, you'll release the balloon. You'll have to make sure that as it goes up, you don't have any payload swing and strike the ground. That is also a little tricky if it's windy. And then while the balloon is in flight, you'll definitely receive at least some information from it. Minimally GPS information telling you where the balloon is located at any given time. Quite possibly sensor data. So in the case of radio sounds, all the data will come down and you don't have to get it back. In the case of the video streaming, you'll also get video stream data during the flight. And then the last bullet point here, the chase, there's an asterisk next to it. That means this is only for the video streaming side. The radio sound side doesn't bother to chase their stuff. They'll just launch new ones over and over again. The video streaming side wants to get their stuff back so they can fly the same stuff during the next eclipse and also get some data logs off of it that weren't sent to the ground by radio. So again, in NEBP, only the video streaming payloads will be recovered. Some comments about flight predictions. Basically, in the case of flight predictions, you tell the software where you're going to launch from, when you're going to launch from, when you're going to launch it, how high you expect it to go, how fast you expect it to come down. You can tune some of these things. You could choose a different parachute to make it come down faster or slower. You could put more or less lift gas in to make it go up faster or slower. And in this case, for instance, the left-hand map is the prediction. It shows a flight from Candiota, Minnesota, going mostly south, somewhat to the east, and then cutting to the west at altitude. And then the little dot right north of Bird Island shows the terminate or burst point, and then it will come down, basically doing everything in reverse, faster as it comes down by parachute, landing slightly to the west of a town called Hector. On the right is what actually happened. So we did this flight, and it more or less did what it was expected to do on the way up, but it never did much of a hook to the west at altitude. And so when it landed north of Hector instead of west of Hector. And here's why. Here is the altitude versus time graph for that particular flight, showing altitude on the left hand in the vertical axis in feet above sea level, and then time across the horizontal axis. So basically, this thing went up at a fairly constant ascent rate until about 70,000 feet, at which point we vented the balloon and stopped it from going up. And then we stayed at close to 70,000 feet for about 25 minutes or so before terminating and coming down by parachute. The prediction software didn't know this was going to happen. The prediction software that we used didn't have a float option. So it said, once you get high enough, perhaps 80,000 feet, you'll definitely be drifting to the west. We never got that high. So in other words, the reason the predictions were off is because we didn't do what we had told it we were going to do. On the other hand, we could have used a different software that would have float phase possibilities, in which case it might have had a more accurate prediction. One more video. So this happens to be segments from a 360 video. The plan is to give the video streaming teams a 360 video so that not only do they send down perhaps slightly lower resolution video during the flight, but they get higher resolution results back as well after the fact. So here we go. So I'm just going to turn down the volume so I can narrate this. The camera here was actually on a selfie stick, which was attached to that box that you see once in a while, but the software erases the selfie stick, which is actually pretty clever. So you don't see the selfie stick, and it looks like the camera is just kind of hanging out above the box and below the balloon. Here we are, launched from southern Minnesota, getting above the clouds, and then we're going to cut to the view in the stratosphere. So here we are in the stratosphere. The balloon has gotten a lot bigger, just looking around. This particular balloon had a vent device in the neck of the balloon. So the next view will show that vent device, and there it is. And the vent device opened and closed and let some of the helium out of the balloon and then cut the balloon away. So the balloon flew off unburst, and then the parachute deployed and everything came down. This can be the most violent part of the flight, but the stabilization in the camera is really quite impressive. And then fortunately, this landed near a road in an open field and was very easy for us to recover. On the other hand, that's kind of a hard bump. And so you also want to make sure that you build things strong enough that they can survive some chaos, some turbulence during descent and hitting the ground moderately hard. Okay, last slide, only to make sure that you realize that these slides are available. You can look at this QR code. And I hope you enjoy Stratospheric weather balloon.